So now we've introduced all the main foundations of quantum mechanics. We have our postulates that we can use to find information about the system. We've set up the Schrodinger equation, and we've looked at our first exactly solvable system, the particle in a box. For the next couple of chapters, we'll be looking at the additional problems that we can solve exactly in quantum mechanics, namely the harmonic oscillator, the rigid rotator, and the hydrogen atom. But many of these problems, in particular the hydrogen atom, don't work very well, or the math becomes much more difficult. It's difficult enough, but it's even more difficult if we try and stick to our XYZ coordinate system. And so in problems where it naturally makes sense to think of things as spheres, like electrons orbiting a nucleus, spherical coordinates are a much more natural system. So we're going to introduce that in this math chapter. So let's go ahead and draw our coordinate system here in terms of x, y, and z that we're used to. So we'll have x, y, and z like this. And if we have a point out here, we can define this in terms of how far it is along the x, y, and z axes, and that tells us where that point is. An alternative way in the spherical coordinates is instead we think about how far is the point away from the origin. We call that r, the radius, if we're thinking of this as a sphere. And then the other ways we need two more variables to define this, where this point is in space, and that is, if we only know the r, that only tells us how far it is away, but doesn't tell us which way it's pointing. And so we need a couple of angles to define that. So the first of these angles we'll define is from the z-axis. We'll call this one theta. So this is the Greek letter theta. That is our angle from the z-axis. And then we need one more angle, and that's the angle from the x-axis, which we will call phi. What we can think of is theta is similar to the idea of latitude. If we're defining points on the spherical surface of the Earth, theta tells us how far are we away from the North Pole, right? So that theta is equivalent to that. Phi would be similar to longitude, and so longitude tells us what angle are we away from the prime meridian, and in our case we take the prime meridian as the x-axis, right? We have to define kind of a special direction, and we use the x-axis as that definition. So if we want to switch between spherical coordinates and Cartesian coordinates, we can define x, y, and z in terms of r, theta, and phi, so we can go back and forth between these. So x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, and z is equal to r cosine theta. We can also, of course, go the other way around if we want to switch from, if we want to find spherical coordinates in terms of x, y, and z. R is equal to x squared plus y squared plus z squared square root. So this is just the Pythagorean theorem to tell us how long this right triangle is. Theta, well, we can define cosine of theta is equal to z over x squared plus y squared plus z squared to the 1/2 over r, essentially. And tangent of phi is equal to y over x. So if we ever need to switch back and forth between these coordinate systems. Now, r, theta, and phi have specific ranges. When we consider x, y, and z, they can take any value, right, from negative infinity to positive infinity, but not so for r, theta, and phi. So r starts at 0. If we're considering the distance from the origin, it can be at the origin. And it can go up to positive infinity. So r can never be negative, because if it's pointed the opposite direction, r only tells us the magnitude, how far it is away from the origin. It doesn't have any direction component to it. It's not a vector. Theta, if we're going from that's our angle from our z-axis, it can go from the positive z-axis to the negative z-axis. So we define it to be 0 if it's pointed along the positive z-axis, and can go up to pi, 180 degrees, right? So pi, we define these in terms of radians. Phi can also start from 0. That's if it's along the x-axis, and phi can go all the way around the whole circle. So its range is relative to is 0 to 2 pi, and this is all relative to the x-axis. All right, so in the next video, we'll look at an example of taking integrals using this coordinate system.